going to work on the ideal gas law for a little while, and then we'll work on another law if we have time today. Okay? So turn to talk to the person next to you. You got 2 seconds to talk about what a theory is.
I guess the first thing we answer is whole semester. It's okay though. Thanks.
All right, back to me. 3, 2, 1, halt. This group up here was talking some good stuff. Tell me what's going on. Theory.
So you were saying it was like a really tested hypothesis?
A very well successfully tested hypothesis. Good. So it's very well supported by many, many observations and many experimentation, data collection points to basically say, like, we think this is true because there's all this data to support it, right? Okay, so that's a good explanation. And the idea is that eventually, once we get all that data, we'll propose this to be the model that describes how natural phenomena occur. Okay, so you're working with me, you're writing down the notes with me, not doing anything else, just be one with me in the notes. I'm doing a quick check out after I get done with this, okay? So the kinetic molecular theory, KMT for short, kinetic molecular theory, is supposed to describe how gases behave, supposed to. So there's all this data to suggest that, you know, some of the characteristics you guys have already described actually exist for the real term here, though, is not just all gases, exists for ideal gases. So we're saying that the kinetic molecular theory describes the behavior of ideal gases. All right, so if you're done writing this part down, I want you to close your eyes and think about that ideal person in your life. Ideal man, woman, boy, girl, whatever. Think about their characteristics. Absolutely. Okay, so if I'm describing my ideal person, so he gets up, he actually makes the coffee for me at night, so it's ready in the morning. That's all. That's all. So he's pretty sensitive, so it's hot in the morning, okay? It's a programmable coffee pot, guys. It's 21st century, okay? He makes sure my clothes are clean, even though I don't put them up. There's stacks of laundry right now. It's been a long week. He helps me train the dogs so that they're pretty good. So Wally, we went to Trader Joe's the other day and got a Kringle. You know what I'm talking about? So it's a big, huge Danish, like huge. We had company over, so we bought this like pastry for the morning. I had like this much out of it, and it was delicious. Like, you should get it from Trader Joe's. It is $8, but it's good. It's $48. And Wally, our Great Dane, got up on top of the stove, ate 2 pumpkin donuts, and the entire Danish. I was like, there was little trails of wax paper and aluminum foil all the time. Oh yeah, I was like, what's wrong with you? Like, your belly's not bulgy. He did have bad gas, but you know, it's kind of what happened. And he totally didn't feel ashamed at all. I held the paper and I smacked him in the face with it. I was like, you see what you did? Like, I'm so mad at you right now. And he was like, it's home, it's worth it. Yeah. So, anyway, my ideal person takes care of the dogs. I wish he would like go running with me, but he doesn't always. So, I mean, I would say like 90% ideal out there.
Yeah, what about yoga?
Oh my gosh, he only went for my birthday. That was it. I'm not going to get it. So, there's one guy's really good instructor. So anyway, what I'm saying is my ideal person is not out there. Okay, I just have to compromise just a teeny bit, just like you're going to have to. Yoga, running. I already explained that. Yeah. Okay, so that whole thought process. The whole thought process out there is just to say that we think that there's ideal people and ideal gases out there. And we want to assume that they're out there. That's the only thing we live for, is the fact that there's an ideal person or gas out there. But there's really not, okay? But we will make all these assumptions that it's out there, because if not, we won't. You guys just report back to me on your ideal person later, okay? So we're gonna go through these 2 pieces of this first, okay? With me, okay? So we assume ideal gases have no volume, essentially no volume, and that makes our lives so much easier when we have to do math. basically we make all these assumptions so our math is easy. If we start to think about the real deal, the real gases out there, the math gets exponentially more difficult. So, and nobody's got time for that. Just like if you think you're real, or if you think your person's out there, you get stressed. No, sorry, if you think that your other person's not out there, you get stressed. Similar situation. Okay. So
you just tried to stress us out of it?
I just burst your bubble, told you the truth. Somebody had to, guys. Okay. So ideal gases have no volume. We basically say that the space they're taking up is negligible or takes it's very, very insignificant. But guess what? Real gases, fill in the blank for me. If ideal gases have no volume, real gases do have volume, right? Okay, so we're basically contrasting the ideal world that we're going to live in for now to the real world that we actually know exists. All right, so ideal gases are assumed to have constant random motion. And with that, I think Mackenzie actually mentioned this part. When they have constant random motion, that means they have no intermolecular forces at play, meaning they should not attract to other particles in the surroundings. But guess what?
They do.
They do, right. Real gases do have non-random motion. So we're making sure we know what the ideal gas hypotheses are, like the postulates that are in black here, but we're then understanding that it's a little unreal world we're going to live in just so our math stays easy. If not, we have to deal with the real gas laws, which are not as easy. There are 5, sorry. All right, so the kinetic molecular theory continues to state that whenever the particles collide, I can't remember who told me this one, when particles collide, we assume, thank you, Austin, we assume that they collide and bounce back, collide and bounce back, collide and bounce back in a very 100% energy transfer manner, meaning that there's no kinetic energy lost in those collisions. But I think you guys saw in your simulation yesterday, maybe something different. Hey, Will, what happened when they collided in the simulation?
I don't know, but like, what would happen is like, I type in 100 as the particle, and it'd go to 99.
You mean the pressure?
No, the particle. The particle would go to 99. Like, it would drop apart. It did.
I believe you. I'm not just saying that.
That's
So we'll talk about the masses shortly. But what you should have seen is that sometimes they would collide and they would come back off like 100% of the speed, and sometimes they collide and come back like slower speed, right? Okay, so yeah, that's what you should have seen. So because real gases have inelastic collisions, meaning that they do have a slight energy loss, and it's usually due to friction. So kinetic energy changes due to friction, because the particles kind of like slide past each other and they can lose a little bit of energy because of that. Now this is true, and I think that, I can't remember if I mentioned kinetic energy, temperature and kinetic energy earlier. I think maybe it was Zoe, I can't remember. But I'm going to go ahead and click this little guy off. Okay, so kinetic energy is directly proportional to Kelvin temperature. Notice that we are dealing with Kelvin yet again. So I will always write that as kinetic energy average is proportional to temperature in Kelvin. And that's actually true for all gases. So this is true yet again for real gases as well. And we mentioned a version of this already as it pertains to motion, like how these particles move with or not with each other. So this little bullet point and this bullet point are related because it elaborates a little bit more on what it means to be random motion. It basically means that they're not going to attract or repel from each other in any way or form. But guess what? Real gases, anybody want to help me out here? Do have attractions. Do attract.
What is that word? Right underneath her word, it's like really
Inelastic collisions?
What's the word I meant to use?
Friction.
Oh, freaking.
They have friction.
So for real gases, it's just make wind?
So yes, so this is the same. That characteristic is true for all gases, ideal and real gases. Okay, give me a quick 3 IMFs, intermolecular forces that we talked about. London dispersion forces. What else? Dipole forces and hydrogen bonding. Okay, which was the strongest of the forces? Okay, and which was the weakest of the forces? Good. So we'll eventually incorporate these again, but it's nice that you guys remember this. So thank you. All right, give me a thumbs up when you're going. Close there. Okay. All right, I'm going to draw a picture, and I think that might be behoove you to draw as well, along with this last postulate. It just means that it's true for real gases and ideal gases. It's true across the board here. All right, so if I have a little particulate diagram and my gases are all here, right? They're colliding with the container wall. What is that causing? Come on, Anna. It's causing a certain pressure, right? So let's say pressure is 1 atmosphere because they're colliding with all the container wall. Well, this is assuming no IMFs are at play, no intermolecular forces. And those are the ideal gases. What if we have the same situation, but these particles are like kind of buddied up and they're attracting to each other? And they're colliding on the container wall still, right? But what happens to pressure here? So you said it questionably, right? Indigo, why does it decrease? Yeah, because lesser number of collisions. So that's why we have to really make our assumptions to be ideal behavior, because as soon as we start realizing that, the real gases exist, we have to adjust for pressure. We have to subtract some form of pressure to make sure we only have the pressure that's actually caused, and that makes things more difficult. Okay, so this was an ideal situation where we had no intermolecular forces, and the other picture that I drew over here has IMF, so has an intermolecular force at play. That's why I've drawn them together. And the pressure decreases just because the particles collide less. So there's a problem with that, and that makes our math a little bit more challenging. Okay. I just said P equals 1 atmosphere. I was just giving a sample example here. P decreases. I was trying to say these things out loud. I'll just keep repeating myself. Okay, I'll try to slow down. Okay. So, well, if you want to take notes on your paper notes, that's fine. If you also want to add to your foldable, it might kind of do both things at once for you. We're going to talk about the ideal gas law after this, okay? Okay, so all of this theoretical stuff is more the explanation based behind all of our mathematics. There's also sometimes a graph that will indicate to you some of the differences in the ideal behavior versus real behavior. So I just want you to look at one thing for me. If this number 1 right here is showing ideal behavior, and all these are up here, they're skewed, right? They're way away from ideal behavior. They're skewed high. But at what types of pressure are they skewed high? Look at the graph. Higher pressure, right? So high pressure is over here at 800 atmospheres and 1,000 atmospheres. So what's going to happen is that the ideal behavior is skewed, or no, let's do it this way. Ideal behavior exists at high pressures or low pressures? Make a choice. Low pressures, right? Because here's the ideal line, right? The gases are really skewed away at high pressures, but they're closer to the line over here. They're somewhat close. So ideal behavior exists at what pressures? Low pressures, right? Okay. I'm going to have you guys go ahead and stand up for me real fast. So stand up. You're not going to be out of. All right, so you're at all the gas, you guys are all gas particles, okay? You're all gas particles, and you're at one particular temperature. Let's say room temperature, so 298 Kelvin. Okay, move around for me. Move around. All right, so you're moving at one speed. Okay, your temperature is now really, really warm. Really warm. Don't run. Just move faster. Move faster. You're literally punched me across. Alright, and the temperature is really, really, really cold. The temperature is really, really, really cold. Okay, really, really cold. Okay, so I don't know if you guys are you guys condensing? Are you condensing? Yeah. Alright, so at this point, listen, at this point you're close to other members of the gases, right? So you have the opportunity to now have intermolecular forces. You have the opportunity to have IMFs. Okay, so director C, sorry? Director C?
I would be a lot. I know. Yes. I freaking love it. That sounds really good. Like, yeah.
All right, come back to me. Okay, guys, thank you. All right, so basically we just demonstrated that you were flying around the room with no attraction to other particles. When you were in high temperature, you were coalescing back together at low temperature. So ideal behavior exists at low pressure and high temperatures. So then vice versa, real gases exist at high pressure and low temperature. Okay, so that's why they're opposites of each other. All right, now we're rolling to the ideal gas law. Okay, so if you want to write it in your foldable or write it in your notes, it doesn't matter to me. I'm going to come right back to this in a second. Here it is. Ideal gas law. Take a minute and write all that information down first. These are the variables that are in the ideal gas law. I'll be quiet so you can write. I'm sorry. It's one of those things I'm going to do.
What is that? Yeah, what is that? It's like a clinking. Something's like hitting something back.
The ventilation. That's what I think you're talking about. Watch your guns, you guys are thinking.
Oh, I can do that.
Atmosphere times M.
Yes, atmospheres multiplied by liters. So yes, this is a huge unit right here. It is 0.0821 atmospheres liters divided by moles K. So this is all in the numerator. That number, atmospheres times liter. It's all the numerator. And then this is all the denominator.
Are we gonna have?
You will use it so much you accidentally memorize
So it's 0.0821
atmosphere liters. Atmospheres times liters divided by moles K. And mel means numerator and then means denominator. Okay, so we've dealt with all these scenario-based questions with like Boyle's law, changing pressures, Charles' law, changing volumes, Gay-Lussac, changing pressures and temperatures. So we went like from scenario 1 to scenario 2. Notice you don't see 1s and 2s here, right? Correct? Okay, so it's not going to be like, oh, here's one pressure and then here's another pressure and here's one temperature and here's another temperature. It's just going to be given to you straight. Here's the pressure, here's the temperature, here's the volume, find the moles. That's what it's going to tell you. So it's very clear when you have an ideal gas law. So PV equals nRT. What's N stand for again? Moles. Because you're not given two scenarios. You're not given two of any variables. Okay, so pressure though, because we have to use this universal gas law constant, what does pressure absolutely have to be in this problem? Atmosphere, right? So if I give you milliliters of mercury, you've got to convert to atmospheres. What does volume have to be in? Liters, right? So you're checking it off here and here. So I give you milliliters, you find liters to plug into the math. If I give you grams, you have to convert to what?
Liters.
Grams, you have to convert to moles. That's amount, right? So that's going to be our mole amount. And if I give you Celsius, you have to convert to Kelvin. Okay, so those units are very particular here because they have to match with the universal gas law constant. Okay, so pull out your 1 through 16 again because we're going to go to 17, 18, 19, so there's only 3 more. On the lecture notes that you guys had a couple days ago. If somebody needs one, please let me know. I only have a couple left. right, so I'm going to go ahead and go to 17. Ready? Okay. I might need to grab a slide here. I'm going to do 17 with you first, okay? What do you need? Do you have money for you?
Yes, please.
Why? Oh, yes. Okay. All right, so 17. Tell me the first given you see, Anthony. You got him for number 17. Do you have the paper? Here, pass that right. Do you have it? Oh, grab it. You don't need this. Grant, tell me the first given. All right, so 425 milliliters is our first given. Everybody tell me what variable that's representing. V for volume, right? Okay. Yeah, so we will have to get to liters. We'll get there in just a second. Of oxygen gas at a temperature of, so what's the next variable, Savannah? So 24.0, yeah, degrees Celsius. Okay. Evan, what's the next variable? Guys, everybody should have this on your desk. If you do not have one, I said let me know. Why, you guys just big chilling? You gonna let me know? Pass that back to Zoe, please. Or no, you want to tell me. Who needs a paper? Okay. Zoe, tell me the next variable given.
0.889 ATM.
And that's our pressure, right? 0.889 ATM. Okay. The next sentence, Will, what's it ask for?
How many moles of oxygen did
Okay, hold on, pause. What's the question?
moles of oxygen?
Okay, so N, you're looking for N, right? Moles. And it does say of oxygen, but this whole thing so far has been talking about oxygen, so that's why I have been labeling them. And then the last question, Jacob? Right, so then we're going to take that to oxygen. Remember, oxygen. It's a diatomic molecule of oxygen, so that's going to be important later. Okay, so as you look now, you'll notice that none of the other laws match except for which law? Ideal gas law, right? Okay. So PV equals nRT. And then you're like, oh, that R. Okay, so what's the R again? What? Give me the whole number. 0.0821. Keep going. Atmospheres times liters over moles times Kelvin. Good. So then we look in the matching of the units. You'll notice that some things don't match. So what does this have to be up here, guys? Tell me the number, though. 0.425. Good. You're bouncing decimal back. How many places? 3 places, because there's 1,000 milliliters in a liter. Temperature must be, what's that in Kelvin? 297 Kelvin. And then atmospheres is good, and moles we're looking for, so everything else matches R now. Okay, so now we're good to plug into the ideal gas law. So like I always do, I don't like to plug in numbers yet because I'm going to have a oopsie butterfingers mistake. So I want to divide everything and isolate in. So what am I dividing by? RT. So divided by R and T on both sides. So what you do to one side mathematically, you do to the other side. That will cancel out R and T, leaving you with N. So N is still moles of oxygen, so I'm just going to label that just so I remember I'm talking about oxygen gas, which is extra fact. So N is going to be equal to PV over RT. That's what I have right here. Okay, what's P? 0.889 atmospheres. Writing your units and all. Do not jip yourself on that. It's the only way you'll make sure you're canceling units. What's V?
0.425.
0.425 liters. I heard liters. Good. Divided by? I know it's a big one. Okay, so 0.0821 atmospheres times liters over moles times K. Yes, you do have to write the units because that's the only way you're going to cancel your units out. It's a big one. Okay, and then T is 2. Guys, come on, help me out here. Thank you. 297 Kelvin. Okay, so we've plugged everything into our math, our work here. Give me one of the units that cancels, Hallie.
ATM.
Atmospheres here and here. Good. Top and bottom cancel. Jasmine.
Meter.
Good. Top and the denominator. Good. And then you'll notice Kelvin, this is weird, like in the numerator on the denominator, you heard me, the numerator on the denominator has Kelvin, and then the denominator of the denominator has Kelvin. So we have one top and bottom, right? So Kelvin and Kelvin cancel. All right, and then this mole is the only thing left, right? So mole in the denominator, when you divide, goes where? Well, math terms. Floppy dot, copy dot. Floppy dotty choppy. Something. The mole comes back to the top, right? Because you're basically multiplying by the inverse. When you divide, you're multiplying by the inverse, so the moles come back to the top. And if you don't understand that, I will help you with the math later, but I'm teaching chemistry first, okay? So, go ahead and calculate. You do need to put this in your calculator. Everybody needs to have a calculator. Let's go. This is ozone door. We put it on Thanks, Zane. Raise your hand if you need a calculator. Zane has made so kind to do that. If you wrote down your math, you should really get your paper. Mine is squished.
So we don't divide anything on the denominator of the denominator.
No numbers down here. So guys, you're putting in your calculator the numerator values, which is what and what? 0.889 times 0.425. Okay, so you're multiplying two numbers in the numerator. Boom, done. Put those in parentheses if you're doing this all in one big calculation. If not, you can take your denominator separately. You can do two separate multiplications and divide at the end. But if you take this, what are you putting in the denominator? 0.0821 and 297. Divide. What's your answer? 0.01549. I'm going to round up to 5 just there, okay? And that's moles, right? Because moles is the only thing I didn't cancel. Moles of what?
Oxygen.
Oxygen. I need a thumbs up to make sure you plug this in your calculator right, because I can teach you the chemistry, but if you can't calculate it, that's on you. Thumbs up if you got this plugged in calculator correctly. Sorry, the tough love comes out with the math, because you guys are like, 10th and 11th grade, you can have this in the calculator. All right, so we have moles now, right? The other question, so we checked, we got moles, yay. What was the other question? Get to grams, so what am I doing here? I heard periodic table and I heard what? Molar masses, I think is what I'm hearing. Okay. And I'm keeping my whole number for now just because I'll round at the end. And this is diatomic oxygen. Everybody, what's diatomic oxygen's mass? 32 approximately. Good. So 32 grams of oxygen per 1 mole of oxygen. And we get what? Guys, you guys can calculate.
0.495.
Good. And I think 366 was what we needed for this whole thing. All right, you guys do 18 math. I love the attitude in this class. The group positivity is really, but it's really different. It's pretty depressing. I'd really like for you guys to focus and be positive about this, because this is one example, and letting you know right now practice on your own. So I'm here for you to make sure you're troubleshooting as you need it. Some of you guys are very good about that. I appreciate you every day. You can work with person right next to you. Guys, warning now, okay? Because you're not doing what I asked you to do. Nicole, you see the other given? It's the first, that's 5 moles, that's in.
Yeah. Was it 760 kilopascal? Or is it 111? Oh, I think I'm right. Yeah, that's there's just no gas. Like, you know what?
I mean, that makes sense.
How's legal change?
Yeah, I just I'm not really sure what you got That's your R. You have to find a variable.
Technically, you go to 20, and then you start over.
Yeah, you have to put that whole little block.
Alright, I hear a lot of little like 19. Do you know how to do 19? Do you know how to do 19? I'll give you a quick tip. So eyes up here if you need it. Shh, just for the second here, okay? So in 19 you're given volume, you're given pressure, you're given temperature, right? And then they give you like 2.62 grams, but you don't know the identity, so you cannot convert that to moles because you don't know its molar mass. And then you read down further, and then what's it asking for? It's asking for what? Molar mass, right? Okay. Anthony, help me out here. What variable do I have to solve for here in number 19? You're looking for N, right? Which means you're looking for moles. All right, so since you're going to look for moles, and you're already given grams, everybody tell me what the units for molar mass are. Grams and moles, right? So you're going to have molar mass, which is equal to grams divided by moles. Okay, so once you get the moles, you already have the grams. You'll simply put the grams, you'll divide by the moles you just got, and that will be molar mass. So it's just using a little bit more in-depth information. Did I clarify that 19?
You're good. You're good. No. Remember to pass out the We'll start first ranking your well, no, on 19, right? Are you on 18? I don't understand. On 18. I have one, but alright. I don't know why that's even there, but so he gave me this. Look at the right, it's your pressure. Yeah, I remember. It's like this is Ours always wait, that's right, go through 20. Go through 20. Right in your notes. Yeah. Alright, so you guys got this, right? You got R. You're good with R. So if you have all of this information, what's the gas law? What's the gas law? And you want to solve for P, right? How do I want to isolate P? Divide by what? I want to get P by itself. Divide by B, is that what you said? No, because P needs to be by itself. We can't, so this is just algebra. You're just taking your isolated variable. So P wants to be by itself, so we divide by V on one side, P on the other side. Okay, when did you guys learn this in math? Well, that's like I think like 8th grade math. Okay, so you're dividing by B, right? So you're dividing by one on one side. You also do it on the other side. So then the B cancels because it's the same variable. So then P is equal to nRT over V. So it equals all this right here. And since you've labeled all these over here, you're plugging those into those spots. Okay. Right. Take about 3 more minutes for your R guys. I'm trying to get longer. I don't think that let me see your work. Question. So I got but when I put that in, it's 66.
I know it's
697.
Right, just a quick survey. Give me a thumbs up if you finished with 18. Okay, keep going. Thumbs up for 19. All right, who's started on 20? Okay, so 20 you cannot finish because I'm not going to be able to teach you the rest of that today because I'm just making sure we're on the same page. So 20, I'm just going to leave you hanging. I'm just going to leave you hanging, okay? All right, so you got like a minute to finish where you are. I have one more slide, 2 more slides I think for you guys, okay? Did you guys do reactions or geometry? Oh, good, good. I'm just not ready to start right now. You guys are totally able to do reactions or BCE and low ratio, and that's it. Okay. All right, so continue working on what you're working on. If you are done, please add this to your notes someplace with the KMT. Add that to your notes.
I feel like it's the most fun. She's right next to me. Oh my god. I'm serious. It's incredible. Like, Olivia. You are smart.
Never math is hard. I think math is hard.
And history.
Okay. History is not bad. I know. You take some class. That's why you said so bad. Okay, actually, if you wrote that.
Yeah.
What? I saw it. I could totally help you with this.
No. just like
Mine's no.
I think I did something just so
I know. By the way,
Huh? Between, decreasing space between atoms.
By the way,
You can use these as or whatever.
The calculus.
So you guys are
What's the issue?
I'm gonna write that out real fast.
Is this the only slide?
Yes.
Alright, so I think most of us are quiet at this point. I know you still may be in the middle of 19. We have about 10 minutes left in class, so I just want to tell you this last slide. I had intentionally had you guys do your simulation yesterday because a lot of the facts we're talking about today, you have that background information now. You have those particles flying around. You know how the variables are relationships. So you should be visualizing these things as they occur. So next week we'll finish up the like 20, which is gas laws with a little bit of stoichiometry involved. So we'll do that next week, and we'll do Graham's law. What was the other law you guys wrote down? Dalton's law. We'll do those maybe next week, maybe after Thanksgiving. But we're almost done with the gas laws. But you will be finishing your foldable at the end of class. So I'm going to just tell you this last thing, okay? No, I mean you won't. I want you to finish working on it some more by the end of this week, but we'll get there. Okay, so we already know that gases have a low density. What's the formula for density? One more time.
mass over volume.
Right, so density is equal to mass per volume. So I can still have like a high mass, but if I have a really, really, really high volume, because they're really highly spread out, the volume being so large makes the density decrease because you're dividing by a big number in the denominator. So they're very spread out, which makes them low density. Yeah.
Do we need to write down that chart?
No, this was just giving you an example. Okay. So, give me 1 second. I'm in the middle of talking right now. Okay. So another thing is that gases, we kind of already knew this already, gases are very spread out, so they can compress, which is going to be something that's quite different than most other things like solids are not going to be able to be compressible because their particles are so close together. So these are two things we already kind of knew, you're just putting into words now. The two words diffusion and effusion, we'll start to use those more when we talk about Graham's law, but who remembers diffusion from biology? Okay, so movement from what to what?
Higher to lower.
Higher to lower areas of concentration, right? So we know that things that they move around, and they move from an area where they're highly prevalent to an area where they're less prevalent. So gases do the same thing. When the particles are moving from high concentration to low concentration, they will then diffuse across the room. So if I brought in a box of Krispy Kreme donuts, you'd smell them. You know, the first people here would smell them, and then the next layer of people would smell them, and then finally Savannah would smell them. But it's because it's diffusing across the room, okay? Now, those particles as they're bouncing around, there'll be some that move like really, really fast, and there'll be some that move kind of slow, and these little vectors, these lines are supposed to represent that. So they have a variety of velocities amongst them. And then effusion, and this is a example here for you, okay? The effusion definition is specific to a closed container. You pop a hole in that closed container, so we have a balloon. Drop a hole in that balloon, and what starts happening to the gases? Right, they slowly start to leak out, right? So that's what this little picture down here is supposed to represent. But there is a method to the madness, right? Most of the time we fill our balloons with what? Okay, so if you're able to go to the store and get helium, you fill it with helium. But if you're just hanging out and you're like, I gotta blow this balloon up, what are you gonna roll carbon dioxide, right? That's coming from your body. So as you pop the hole in the balloon, these gas particles can start to effuse, which is them moving out of the container. So I want you to tell me, do you think helium or carbon dioxide would come out of the balloon first? Confident people, come on. Okay, you still have a couple minutes with me. Can you guys stop packing up for just a minute? Because some people are nearby. I'm going to have you put your laptops up. Just hold on. Okay, so I heard helium. Why? Okay, tell me more about helium. Everybody look at the periodic table. What's helium's mass? Can you see that?
1.01.
It's hydrogen. You're close, you're close. Okay, 4 grams per mole. Okay, quickly add up carbon dioxide's mass. 44 grams per mole, thank you. Okay, so, okay, you with me? I'm back over here. Okay, so look up here, I have a little relationship for you. So kinetic energy is equal to half of mv squared. So as the mass is large, so the kinetic energy is a constant at our temperature, we kind of already spoke to that. But as the mass increases, the velocity has to decrease, which you guys saw in your heavy particles and your light particles in your simulation, right? Big things move slow, little things move fast. So the helium's going to come out first, the carbon dioxide's going to come out last because it's so heavy. So if you want a balloon to last forever, what are you going to put in it? You want it to last forever. CO2 is going to stay in the balloon. The helium's going to be out in an instant. Okay? Helium just makes it float, which is cool. Okay? So go ahead and put laptops up for me, okay? Laptops up. Log off your laptops. Log off your laptops.
Always nice. Always
That was hydrogen, though, yeah.
It's fine, guys.
It's half full. Gotta be optimistic. Okay, I know you're not laughing. Sorry, never mind. Oh man, I was like 70. I was like, that's fine. Yes. I was like, I ran away from everything. And I was like, it's a vlog. I needed that one. I saw a dog and it's sticking in his head and I yeah, Anthony, we literally were talking for like half an hour. Alright guys, so to conclude, last thing, 3, 2, guys, ladies and gentlemen, 1, thank you. Give me a thumbs up if you've already spoken to your scientist, your selfies with science person. Okay, good. A couple of you guys are waiting for communication back. You can CC me on everything, okay? You can CC me on everything. That way, if you have a question, I'll try to answer you back personally. Ladies, Mackenzie with me? Thank you. Okay, so other than that, homework is kind of just wrapping up some of the things you've been working on. Okay, so finish up some more in your foldable. We just finished with 19, 1 through 19 now. Okay, I will take questions Monday, I guess now for 1 through 16 because we spent some more time here. But overall, do you feel okay with gases?
Yeah.
It's all algebra. It's all algebra. Okay, it's been better probably than other things. Okay, and then I have PS 14 due later, so just make sure you kind of keep an eye on where things are due later on in the teaching. Okay. Thank you.
So what do you